Modern physics is trapped in an epistemological crisis caused by a severe structural incompatibility. On one side, we have general relativity, which models reality as the curvature of a smooth, continuous space-time manifold. On the other, we have quantum field theory, which dictates that matter and forces are discrete, quantized excitations of energetic fields. When standard analytical solvers attempt to bridge the gap between continuous space and discrete particles, they break down. The dimensional mismatch generates computational failures, yielding infinite paradoxes or mathematical divergences rather than coherent answers. The theory of infinity, or TOI framework, approaches this problem differently. Instead of retreating into unprovable higher-dimensional architectures like string theory, TOI treats this exact continuous discrete dichotomy as a strict operational boundary. Within this framework, physical constants and scaling laws do not exist as static numerical values floating in a void. They emerge dynamically from the active interaction of distinct mathematical modalities operating across that boundary. To resolve these persistent paradoxes, we have to stop treating mathematical equations as inert rules. We must model them as active physical transport mechanisms, tasked with carrying information across a dimensional border. To evaluate how a continuous exponential integral crosses this border and maps to a discrete geometric ratio, the TOI compiler architecture uses a specific logical structure called the tripartite morphology of modal transport. This diagram illustrates the three distinct components of that transport mechanism. First is the material cause, formally defined as the Wurm. This represents the bounding continuous manifold, the spatial geometry, or the exact domain over which we are integrating. Second is the efficient cause, defined as the Wurm. This is the active, stateful mathematical operator designed to ingest an algebraic payload, tunnel through the continuous manifold, and carry it across the dimensional rift. Third is the final cause, or the Wyrm. This is the absolute, unchangeable topological invariant, the mathematical attractor sitting at the bottom of the phase space that actively pulls the payload toward resolution. We are going to stress test this exact transport engine. We will observe how mutating the continuous spatial geometry of the Wyrm radically shifts the discrete mathematical attractor from the golden ratio to the Tribonacci constant. By fracturing the spatial metric, we force the mathematical system to mutate its own foundational sequence limits. We begin with a baseline control test. We evaluate the continuous exponential transport function over a simple, linear spatial geometry, y to the power of 1, bounded by the unit interval. Applying standard calculus to integrate this continuous exponential function naturally yields an exact complex transcendental volume. To extract a discrete invariant from that continuous field, the framework applies the Euler-Golden shadow approximation, mapping exponential behavior back into a discrete algebraic space. This proxy truncates the infinite transcendental tail of the growth curve, bounding it safely inside a calculable fourth-degree polynomial cage. When we substitute this proxy into our evaluated integral, the structural properties of the golden ratio allow the higher polynomial powers to collapse smoothly into linear combinations of integers, following the strict recursive rule that phi squared equals phi plus 1. The scalar output of this linear integration reduces flawlessly to 3 times phi, a perfect 3-phi tautology. When the spatial metric of the underlying manifold is linear, the mathematical operator scales perfectly, preserving the standard two-step Fibonacci recurrence relation without experiencing any structural fracture. Now we execute the stress test. We mutate the spatial argument of our transport function, reducing the integration variable from a linear integer to a fractional geometry, y to the power of 0.5. This geometric reduction immediately breaks the standard linear pipeline. The operator can no longer ingest and pass the payload simply. The calculus forces it to execute integration by parts to resolve the fraction. The mechanics of integration by parts intrinsically injects higher-order polynomial denominators directly into the evaluated output matrix. Within the TOI ontology, the accumulation of these denominators acts as mathematical friction. It represents a latent physical tension generated by forcing the payload across a fractured metric space. We then apply the exact same Euler-Golden shadow proxy to this new highly complex output, dragging the evaluated volume back into the discrete algebraic modality. The integration proves that fractional spatial geometries generate active structural tension, forcing the underlying dimensional face space to warp and expand. This chart compares macroscopic mutations between pathways. The linear control strictly bounds its volume against the baseline 3π multiplier. Conversely, mutating spatial geometry to a fraction radically accelerates the exponential curve, massively expanding the phase volume toward a completely different invariant attractor. The transport operator has jumped entirely out of the two-step Fibonacci family. The calculation anchors onto a perfect geometric projection of the Tribonacci constant, the mathematical limit of a three-step recursive sequence. The spatial geometry dictated the logic of the entire system. A fractional reduction physically forced the continuous integral to upgrade its recursion from a two-step universe to a three-step universe. The TOI framework enforces strict epistemological governance over these findings, requiring us to acknowledge one specific mathematical caveat. The Tribonacci projection carries a beta gap residual, a minute deviation of 0.007 from the theoretical constant. Standard numerical solvers dismiss this gap as arbitrary trumpation noise caused by the algebraic approximation. However, the TOI operates under the conservation of modality rule, which dictates that structural artifacts lost in a projection are never truly discarded. They are conserved as latent tension. That tiny residual is a lawful, positive phenomenal signature. It proves the contextual tension operating at the boundary between the continuous exponential curvature and the discrete algebraic plane. Because the linear integral resolves with zero residual, the framework categorizes it under the apex epistemological status, sealed exactness. Because the fractional integral carries boundary tension, it receives the classification of monitored fate check. It acts as a diagnostic guardrail, representing a highly precise geometric phase mirage rather than a sealed limit. Mathematical ontology requires us to distinguish absolute invariance from the active, tension-filled shadows cast onto a fractured metric. The mechanics of this mutation establish a generalized predictive model for continuous scaling across dimensions. If reducing the spatial geometry to y to the power of 0.5 mutates the sequence limit to the three-step Tribonacci constant, then generalizing the space further down to a cubic root, y to the power of 0.33, forces sequential integration iterations that logically project a four-step Tetranacci limit. This mathematical behavior exactly mirrors applied physics, specifically how continuous quantum fields undergo spontaneous symmetry breaking when their underlying metric is fractured, shifting the physical system into higher dimensions. We see identical analogs in biology. The mathematical model of fractional constraints demonstrates exactly how a biological system transitioning from standard 2D surface expansion is forced into complex 3D volumetric folding. Mathematical boundaries are not terminal endpoints, they are active topological generators. The fractional stress placed upon continuous space drives the morphological complexity of our reality.